Welcome to
Nay.
Do it.
Channel Everyone. Okay, so today we are diving into traffic. Not the annoying kind when you're late, but the fascinating kind inside a computer. We're talking about AI controlling traffic lights.
That's right. This episode looks at a specific study, a systematic analysis of reinforcement learning controllers for signalized urban corridors. In simple terms, teaching AI to manage a string of traffic lights down a busy road.
And it's not just about making one light smart. It's about the whole system. The big question is, how do you coordinate them? Do you need one big brain in the cloud, or lots of little brains at each intersection?
I love that. Big brain versus little brains. So JJ, they compared different setups. Centralized, decentralized, and something called parameter sharing. What's the basic idea?
Think of it like management styles. Centralized is one supercontroller with a God's eye view, making all decisions. Fully decentralized means each intersection has its own AI agent, operating independently. They only see their own local traffic.
And parameter sharing is a clever hybrid. Each junction has its own AI, but they're all identical twins. They were trained together, sharing knowledge and experience. Even though they operate separately, it's like having a hive mind of local controllers.
So they all went to the same school, and you compared them to a classical method, Max Sprecher. What did you find? Who was the best student?
It's not about a single winner. The study used a concept called the capacity region, which is like mapping the network's breaking point. How much traffic can it handle before total gridlock? They compared how these different controllers expanded or shaped that region.
The key finding was that the parameter-sharing decentralized controller performed very well. It matched or beat the fully centralized one in many scenarios, which is surprising and efficient. You get coordination benefits without the complexity of a single central system.
That sounds like a great hack, but here's my question. You train these AI twins on a specific corridor, with, say, 5 lights. What if the city expands? Can you use them on a corridor with 10 lights?
That was a brilliant part of the study. They tested exactly that, generalization. They took the parameter-sharing controller trained on a small network and deployed it on a larger one. The junctions weren't formally talking to each other. They just used their identical training.
And did it work, or was it chaos?
It worked, and something interesting emerged, even without explicit coordination. The traffic started to self-organize. You could see patterns of green lights propagating down the road.
A green wave.
Exactly, a self-organized green wave. It suggests the local AIs, with their shared training, can implicitly create coordinated flow. It's emergent coordination.
It's a promising result for real-world deployment. You could train a robust controller in simulation on a manageable piece of a city and potentially scale it up with less retraining. It's more flexible and resilient.
So to wrap this traffic jam of ideas, this research shows a smart path forward. Not one big fragile brain, but a team of well-trained, identical local brains that can work together, even on bigger problems than they were originally taught. It's a systematic way to build smarter, more adaptable urban AI.
And it critically compares methods, which is what good science does. It's not just about the flashy result, but understanding the trade-offs between different architectures.
Precisely. It provides a framework for thinking about AI control in complex networks, beyond just traffic.
Fantastic. Thank you so much, JJ, Jiyoung, for breaking down the signals on this one. And thank you for watching. We'll see you next time.
Thank you.
Thanks, everyone.